HAZAP is capable of doing several things. So in general, treat phenomena at the atomistic scale, so nanophenomena. It can compute a set of electronic, thermodynamic, and magnetic properties. It can model chemical reaction and dynamics between atoms, characterize material strength. Specifically, it can calculate the bulk modulus to understand how strong is a material. With HAZAP, we are able to compute vibration and phonospectra, material absorption, and the electron function. There is also the possibility of performing molecular dynamic simulations with which we can then extract the diffusion coefficient, have information about atom drifting in the material, and so on. We can also compute electronic transport properties. And as I said before, we have a video dedicated to it on our YouTube channel. So HAZAP has a graphical user interface and is a ready-to-use software in the sense that it's very easy to install it on all platforms, at least all major platforms, so Linux, macOS, and Windows. And it features powerful solvers, specifically SIESTA, Quantum Espresso, and Transista. Now, SIESTA, you see there, SIESTA is in bold because today we will focus mainly on this solver. I'd like to mention that you might be already aware of it, if you're here, that in these days, the SIESTA School 2024 has been held online. And so this school is designed for people who wants to learn more about SIESTA, how to approach to this code, and also the latest features that have been implemented in it. So if you might already know that every time you need to perform a SIESTA calculation, or for this, any type of DAT calculations, you need to define your problem, so the properties that you want to calculate for a specific system. Then you need, in SIESTA, to have the pseudo-potential, which are files that need to be included in the calculation folder and describes the core electrons, how the core electron affect the system. Then you have to set up the basis set, which describes the valence electron on your system, and the decision of using one basis set or another as basically gives you more speed or more accuracy in your calculations. So it's a trade-off, and whether you want to favorite one or another, then you need to be able to set up this basis set properly. And in general, there are many other input file options that can be set up, and the user needs to be aware of all of this in order to perform a proper calculation. Finally, you need to have most likely access to a supercomputer in order to run your calculations, retrieve the results, and perform some post-processing on those results. Some of these post-processing can be already made by some tools that SIESTA is providing, and some other needs to be done by using a homemade script. Well, all this is basically implemented in HAZAP. HAZAP facilitates the use of the code up to the point that you can forget many of those things, and you can think about what you really want to do in your calculation. And you will see in a moment how this is done. This is the main screen of HAZAP, so how it looks like. You see that for each line is a project. And if we go from left to right, we see that there is the system, which is the first thing that needs to be initialized. Then we have the project definition, type of project, and the parameters specifically for the specific project. Then the calculator setup. User can choose which calculator and which parameter. And the run button, it helps to run the calculator, the calculations locally on your machine or on a remote cluster. And after, when the calculation is completed, there will be the user will be also the user can also access the analysis widget and basically see the output of the calculation. So let's move on. So let's look a bit more in detail about all these steps. So the first step is the definition of the structure. This can be done mainly in two ways. So one is creating the atomistic model from scratch. We have a set of tools in order to create molecules, surface, bulk, nanotubes, nanoribbon, and clusters. Or the user can also import pre-existing structures from a wide variety of file format: XYZ, CIF, SIESTA output file, PDB, and so on. It's not finished. The user can after modify the imported structure or the created structure, and different kind of structures belonging to different projects can be merged together. What you see here is on the bottom right is a structure for electronic transport calculation. So you have electron on the left, electron on the right, and at the center, the scattering region. This has been created by using ASAP. And this is a fast view on the different builders. So we have a database of molecules. We have the possibility of building bulk from scratch. You say which elements you want, and ASAP is going to suggest some lattice structure that you can further change. Icosahedral cluster can be easily created, as well as surfaces. Surface tool is quite interesting for me. It's quite nice because before you select a bulk and then you cut this bulk along the direction you prefer. And then it's possible also to create, with just a few clicks, nano ribbons and nanotubes. The next step is, as I mentioned before, define the project type and the parameters. Here you see an example of here you see the list of project. And in this case, the single point project was selected. And here on the right, you have the parameter widget. And you can, in properties, select which properties you want ASAP to calculate for you. In this case, we highlighted the band structure parameters, and you see here on the right that this is a 3D visualization of the path in K-space. This is completely suggested by ASAP. So once you have your bug structure, ASAP will tell you, okay, this is the path. You can always modify it anyway, but it's good because ASAP is going already to give you the coordinates of the high symmetry point. Before you saw a long list of projects, so I'd like to go fast through each of those. So we have a single point project, which is used in order to, in general, to get electronic structure properties, the energies of the system, so total energy, HOMO-LUMO, Fermi, density of states and projected density of states, band structures, charge analysis, work function, we will see later. We have two tools specifically designed for SIESTA in order to converge to quantities. So the number of K-point, Brillouin sampling, and the mesh cutoff, the real space grid. We have a tool in order to, a project, to optimize the geometry of the system, to get the equation of states, so to find out basically the equilibrium volume and the bulk modulus. Another project, local density of states, designed to get information about the density of states in real space, and many more. We have two designed for, among others, to get mechanical properties. Those are two molecular dynamics project type. One is specifically designed for SIESTA, and so it works only with the SIESTA algorithm. The other is more general, so is working for any kind of solver, calculator that you selected. Then we have two projects, nudge elastic band and vibrations. So with nudge elastic band, it's possible to get information about reaction path, reaction energy, activation energy. So basically characterize chemical reactions. And we have also a project to extract the vibrational modes of the system. For material science and photonics, we have two projects, one for calculating phonons and the other optical response. So optical absorption, the electric function, and refractive index. Two additional projects are designed in order to get here the interaction energy, so the contribution to the total energy caused by the interaction between two systems. And this one on the left is called interface analysis tool. Is particularly useful when you want, for example, to extract the energy profile of two systems, which can be used then to extra parameters to get, for example, force field that can be used for molecular mechanics. And finally, we have those projects designed to get electronic transfer properties of a system. And as I already said before, those project has been described in our previous webinar, which is now on our YouTube channel. Next step is to decide the kind of solver, type of solver. So now, and I'm glad to tell you that we support SIESTA 5, which is the latest release of SIESTA, together with the other version of SIESTA, TransSIESTA, and Quantum Espresso. This is the view of the calculator widget, so from which you can select the parameters of your calculator. This is for SIESTA. So as you see, we divided the parameters in different sections: physics, convergency, basis set, SCF. And it's very easy to set up the parameters here, and it avoids conflicting variables, inconsistent parameter settings, typos, and so it's very easy basically to run SIESTA calculation using this tool. However, it's always possible for the user to enter directly in the input file and fully customize it. I'd like to say a few words about pseudo potential and basis set, because those might be problematic settings, okay, when someone is start a new calculations. And pseudo potentials files of each atom species of a system are necessary in order to perform SIESTA calculations and describe basically the effect of the core electron in your system. Those files needs to be generated by the user or needs to be downloaded from a database. In SIESTA, we provide this data, in ASAP, sorry, we provide this database. So the user doesn't have to think about it. It can obviously change these settings, but by default, the user has nothing to do, because ASAP select the pseudo potential automatically. Same goes with basis set. We developed in Simune our own set of basis set, and those are the default one for, but the user can change, obviously, as I said before, the parameters. But again, this is very useful because in principle, the user can somehow forget about these settings and just perform the calculation. Run. Okay, where can we run? Well, you can with ISAP, you can run locally on your machine if you have a version of SIESTA for your architecture, or you can run on a remote cluster. So imagine you have a remote cluster, you send the data, then the connection can be you can disconnect basically from the cluster. Some calculation might take hours, so you can just close the PC, close the connection, and reconnect in a few hours. You can go, for example, for a coffee, get back to your desk, reconnect again, and retrieve the results. So no results are lost, even though the connection is closed between your machine and the cluster. And finally, we have the analysis tools. And in this case, we show the band structure analysis with the density of states. I'm going to go fast because we will look at this more in detail later. So from our webpage, you can ask a trial of ASAP. So if you go in simuneatomistics.com/ASAP, you can click on try ASAP for free, and you can try ASAP for free for 1 month. If you if you request a trial and you download ASAP from our webpage, you will have an installer for your operating system. So it can be, as I said before, Linux, macOS, Windows, and a product key valid for 1 month. Moreover, you will also receive a set of completed projects. So those are projects that can be directly opened from ASAP, and they are completed projects, so you can see the whole workflow, including the results. You will also have a PDF containing information about those projects, so you can understand better what has been done in those projects. Moreover, there is a user ASAP user manual. We have an online version that you can find at docs.simuneatomistics.com, as well as a PDF version, which is shipped with ASAP. And in there is the all information about how to use ASAP, set up project, and basically everything. There are a lot of screenshots, so it's very easy to basically, with that manual, to learn how to use ASAP.